So, temperature can be defined as the relative measure of hotness or coldness of a body. Three main units which you have to understand and know that they are interchangeable. That is, one can be converted into another by just some mathematical transformations. So, volume expansion is simply when you're giving temperature to any object, the increase in its volume due to the temperature you have provided is known as volume expansion. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we are going to start a new chapter here today, that is thermal properties of matter. This is just an introductory class to thermodynamics itself. So before studying anything about thermodynamics, we need to know a few basics that we will discuss in this particular chapter. So to start things, we'll start with what temperature actually is. So when you go to a doctor or when you go to any physician or even your grandmas and grannies, they will just keep their hands on your forehead and they'll be like, okay, oh my God, you have a slight temperature. Oh my God, you're having a slight fever. So how are they understanding that you have a fever? So they're doing this by understanding that you have a variation in your temperature. Just by keeping your hand or using a thermometer, you can just say that, okay, you have a difference in temperature. So what exactly is temperature? That is the first thing we are understanding here. So, temperature can be defined as the relative measure of hotness or coldness of a body. That is, relatively how much hotter or colder that particular object is. That particular measurement is known as temperature. And generally, the instrument used for this is known as a thermometer, which you are very familiar with. So, the device used to measure temperature is known as a thermometer, and temperature itself means that it is the relative measurement of hotness or coldness of a body, that is known as temperature. And in SI units, we can see that in SI unit, the SI unit of temperature is Kelvin, which is indicated by the capital letter K. So, the SI unit of temperature is indicated by capital letter K, that is Kelvin, in order to honor the great scientist Lord Kelvin, who contributed a great deal to thermodynamics, including finding the absolute temperature limit that we'll see very soon enough. So that particular scientist, Lord Kelvin, is honorated here by giving the SI unit as Kelvin, that is K. Now the very next thing, even if you have a fever, the doctors won't say that, oh my God, you're having a fever of 212 Kelvin. They won't say that, oh my God, you are having a fever of 300 Kelvin. They'll just say that you have a fever of, let's say 98. You have a fever of 98. Okay, but then again, if you're boiling water and you're keeping a thermometer inside that particular boiling water, you'll say that, okay, I already know that water boils at 100 degree. Then how is it that I'm having a fever of 98 degrees, but water boils at 100 degrees? I mean, if this were the same temperature ranges, then I would be boiling inside, right? So why is that not happening? It's very simple, because the units for this is different. One is measured in Celsius and the other one is measured in Fahrenheit, and we already know the SI unit of temperature, that is Kelvin. So there are three main units which you have to understand and know that they are interchangeable. That is, one can be converted into another by just some mathematical transformations. So let's start with some quantities we already know. That is, we are used to seeing Celsius in order to measure temperature throughout this particular lifetime. So let's start with that only. So we do know that water boils at 100 degrees Celsius. Water boils at 100 degrees Celsius. But what about Fahrenheit? At what particular degree Fahrenheit does water boil? Then we can say that Fahrenheit will be 212 degrees Fahrenheit. That is, at 212 degree Fahrenheit only will water boil. And what about Kelvin? In Kelvin scale, we can say that water boils at 373 Kelvin, or simply to be more accurate, we can say that it is 373.15 Kelvin. So 373.15 is the accurate measurement. Now, what about the freezing point of water? We say that, okay, water freezes at 0 degrees Celsius. 0 degree Celsius. But what about for Fahrenheit? In Fahrenheit, we can simply say that water freezes at 32 degree Fahrenheit, which means that when Celsius is 0 degrees, Fahrenheit will show a value of 32 degrees Fahrenheit, and Kelvin scale will show a reading of 273.15 Kelvin. So 0 degrees Celsius will be equal to 273.15 Kelvin. And these are the different temperature scales that you have to understand. So one more thing, what if they give you a different temperature and ask you to convert into another scale? For example, they are giving you 38 degrees Celsius. Now convert this into Fahrenheit, or simply they are giving you 96 degree Fahrenheit. Convert this into degree Celsius. So what if they give you a different temperature scale and ask you to convert that particular temperature scale into another scale? So how do you do that? So again, if they give you any reading in some other temperature scale, how can you convert it? You can convert it using the simple formula that is given. For example, if they are giving, okay, convert this much degrees Celsius into Kelvin scale. Let's say 20 degrees Celsius or 200 degrees Celsius. Convert 200 degrees Celsius into Kelvin scale. How can you do that? So simple, you just have to add 273.15 to that particular number. So you will get a net output of 200 plus 200, 400 plus 73.15, that is 473.15 Kelvin. So 200 degrees Celsius can be converted into Kelvin just by adding 273.15 to it. Now what about this particular temperature? Let's say 36 degree Celsius. Convert this 36 degree Celsius into Fahrenheit. How can you do that? So again, only thing you have to do is that multiply this 36 degrees first with 9 by 5. Then add 32. Then you will get your readings in Fahrenheit. So you will get the value as 89.6 degree Fahrenheit. So you can convert degree Celsius into Fahrenheit using this particular formula. And again, if they are giving this particular result, that is, if the temperature scale is given in Fahrenheit and you are asked to convert it into degree Celsius, what will you do? Simple thing, you just have to rearrange this particular equation. If you rearrange this particular equation, you will get in Fahrenheit. That is, for example, if 9 by 5 C plus 32 is equal to the Fahrenheit reading, right? If you want the Fahrenheit reading, then F minus 32 all into 5 divided by 9. Then you will get the reading in degree Celsius. You just have to rearrange the equation in order to get or simply convert one temperature scale into another temperature scale. So using these two equations, you can convert these three scales from one factor to another factor, that is interchanging those particular values. Now the next topic is very simple, that is known as thermal expansion. If you have taken your lunch in a steel lunchbox, then you know for sure that the hassle of opening that particular lunchbox. But the same lunchbox, when you give it to your mom, she opens it very easily. So if your mom is slightly weak and you can't just rip open that particular steel case, the thing they do is that they slightly heat up that particular steel vessel so that you can easily pry it open. So why does this happen? This happens because the property of metals to expand under thermal conduction, or simply we say that when we give thermal energy or simply heat to a steel vessel or simply any metal, that particular metal will change its dimensions. That is, it might change its length, it might change its volume, it might even change its area. So the metal altogether in itself will expand. So that particular property is known as thermal expansion. That is, when you give thermal energy to a system, or simply if you heat up any metals, that particular quantity will expand. It will change its dimensions, and that particular phenomena is known as thermal expansion. So in one word, you can define this as the change in dimensions of a body due to increase in its temperature is known as thermal expansion. Now, we have to categorize this particular thermal expansion into some categories. Mainly, we can see that this particular thermal expansion can be categorized or can cause linear expansion. Linear expansion, which means when you heat up a metal rod, like this one, it can increase its length, not by 1 meter or 2 meter or 5 meters, but maybe minute amounts. Even if it is in minute amounts, let's say in millimeter amounts, it is still an increase. And if the length factor is increasing, we say that that particular expansion due to thermal energy absorption is known as linear thermal expansion, or simply linear expansion. And similarly, if you're heating up a sheet of paper, a metal sheet of paper, it will increase lengthwise and breadthwise, which means it is increasing in area. So we can see that there is area expansion. And finally, if you heat up a cube, let's say a steel cube, and you're heating it up, then lengthwise, breadthwise and heightwise there is an increase, which means that it is a volume expansion. So you have linear expansion, area expansion and volume expansion. Now, we'll just see what all these three incredible expansions mathematically mean. So first, let's start with linear expansion. So what exactly is linear expansion? We can say that linear expansion is nothing but when you heat any metal, the increase in its length is known as linear expansion. And how that particular increase in length happens, that particular increase in length will be directly proportional to the change in its temperature, or simply how much of a temperature we are giving, linear expansion will be directly proportional to that particular temperature. and we can just define it as increase in length of a body of unit length when temperature is increased by 1 degree Celsius. Mathematically, we can write it down as delta L is directly proportional to L delta T, where L is the initial length of the object. And then we can see that to avoid the proportionality sign, we can introduce a constant of proportionality that is known as alpha. Alpha L delta T. So what exactly is this alpha? Alpha is known as coefficient of linear expansion. So alpha is known as coefficient of linear expansion, and alpha will have a different value depending on the metal you are choosing. If you're choosing steel, it will have a definite value. If you're choosing copper, it will have a definite value. If you're choosing any other metal, it will have a different value. So depending on the metal, the alpha value will absolutely change. So it depends on the metal you're using, but the relation still stays the same. And if you want a relation just in terms of alpha, you can say that alpha will be equal to delta L divided by L delta T. So that is the definition of alpha, or in words we can just say that so we can define alpha as the increase in length of a body of unit length when temperature increases by 1 degree Celsius. The initial heading I told you is for specific case of alpha, that is, if unit length is increased by raising temperature by a unit amount, that is 1 degree Celsius is reached, then we can say that that is the explanation or simply the definition for alpha. And for linear expansion, we can just say that, okay, if temperature is increased, the increase in temperature causes an increase in length. That is known as linear expansion. So, linear expansion can be explained as the increase in length of a body due to the increase in temperature. That is known as linear expansion. And if this happens in unit amounts, that is 1 degree Celsius is increased, which is causing an expansion of one length, that is 1 unit length, then we can say that that particular expansion will give you the definition for alpha. So similarly, we can define what is area expansion and volume expansion. So the next thing is area expansion. So what exactly is area expansion? So when you apply temperature to any body, the increase in area because of that increase in temperature is known as area expansion. And we can say that this particular area expansion, that is delta A, will be directly proportional to A delta T, where A is the initial area of the object we are choosing and delta T is the change in temperature and delta A is the change in area. Or simply we can avoid the proportionality constant and simply say that delta A will be equal to beta delta T, where beta or simply beta is known as the coefficient of area expansion, the coefficient of area expansion, and is defined as, that is, it is defined as beta is equal to delta A divided by A delta T. So beta is defined as the increase in area of a body of unit dimensions when temperature increases by 1 degree Celsius. Again, you're just giving unit values to all these quantities, and then you will have a definition for beta, which is known as the area expansion coefficient. Similarly, and lastly but not leastly, we can also define what is volume expansion. So volume expansion is simply when you're giving temperature to any object, the increase in its volume due to the temperature you have provided is known as volume expansion. And again, we can simply say that delta V will be directly proportional to V delta T, where V is the initial volume of the object you have chosen, and delta T is the change in temperature and delta V is the change in volume. So we can just say that delta V is equal to, again, a constant of proportionality. Here this time it is gamma, and gamma is known as the coefficient of volume expansion. So gamma V delta T. So this equation will give you, in order to find what is the change in volume due to thermal expansion or specifically volume expansion, we can find the volume expansion through this particular relation, and gamma again can be described as or defined as delta V divided by V delta T, or simply giving, by giving unit values to these particular variables, you will get a definition for gamma, that is coefficient of volume expansion. And again, volume expansion just means that the increase in volume of a body due to the increase in its temperature. And we can just see that alpha, beta and gamma will all have the same SI unit, and that is Kelvin inverse. So all of these quantities will have the same SI unit, which is Kelvin inverse. Now, one more thing, we learned about what alpha, beta and gamma is, but we still don't know how they are interrelated. If I increase a body's temperature, then automatically its size is changing because of expansion. So again, is it just linear expansion? Is it just area expansion or just volume expansion? Or are they interrelated? If I heat up a cube, automatically the volume is increasing, but evidently it also means that the area and the length factor is also increasing. So is there any relation between alpha, beta and gamma? Let's find out. For this particular experiment, in order to find what is the relation between alpha and beta, I'm going to take a square sheet, that is a metal sheet, which is having an area of A, which is having a sides of L. So when I heat this particular metal sheet, it expands in all directions uniformly by a length increase of delta L, which will cause an area increase of delta A, which means the sides initially will have a length of L and area of A, but then it will increase by delta L on the sides, and the entire area will have a small increase in area, that is known as delta A. So first we are going to write down what are the initial quantities we already know, that is delta L is equal to alpha L delta T and delta A is equal to beta A delta T. That is the equation number 1, which is for linear expansion, and 2, which is for area expansion. And now, in order to find a relation between these two, I am taking one more definition, that is delta A, that is change in area, just means that it is the final area minus initial area. The final area minus initial area will give you the change in area. Area of a square is very simple because it is length times breadth. Here length and breadth will be equal, that is why it is known as a square. So again, L plus delta L is the final length value. So we can say that L plus delta L whole square will be the final area, and initial area will be just L square. So we can say that this particular quantity, that is L plus delta L whole square is nothing but A plus B whole square. So we already know that A plus B whole square is nothing but A square plus B square plus 2AB. Just like that, this particular quantity, that is L plus delta L whole square, will be equal to L square plus delta L square plus 2L delta L. So you have L square plus delta L square plus 2L delta L, A square plus B square plus 2AB minus L square. So again we can see a plus L square and a minus L square, which means these two quantities will cancel each other out, and the remaining quantities are simply, that is, change in area is equal to this one. So the remaining quantities are only, so again the remaining quantities are only delta L square plus 2L delta L. So again there is one more consideration we are taking. Since delta L is already very small, delta L square will be even smaller. For example, if you're taking any small quantity and if you square that particular quantity, you will get an even smaller quantity. So delta L already is very small, which means delta L square will be even smaller. Since it is very small, we are saying that delta L is approximately equal to 0. So since delta L is approximately equal to 0, we can see that delta A now will be equal to 2L delta L. And that's it. Sir, is that a relation between alpha and beta? No, right? So what we do is that we substitute the known value, that is delta L, we have a relation here, delta A, we have a relation here. So that particular relation we substitute into delta L and delta A. So we will have a clear relation. So delta A is equal to beta A delta T, which is equal to delta L is equal to alpha L delta T into 2L, which means that this will be equal to beta A delta T, and delta T will cancel each other out, and the only remaining quantities will be 2L into L into alpha. But what is this L into L? L into L is L square. L square is already known, that is the area of this particular square. Since this L into L itself is area again, we can just say that beta A will be equal to 2 times alpha into A, or simply this area terms will cancel each other out and only beta is equal to 2 alpha will remain. And we have our relation, that is beta is actually equal to 2 times alpha. That is our first relation. Now again, if I don't do this for alpha and gamma, gamma will be left out and he will be very sad. So just for that particular sake, let me assume that I am taking a relation between alpha and gamma. For that, I am assuming that I have a perfectly good cube which is having sides of L and a volume of V. So I have a cube which is having all 3 sides, that is L, and which is having a volume of V. So this particular cube, I am heating it up so that it expands in all directions equally with an increase in length by delta L, and the net increase in volume will be delta V. So this particular cube is now expanded into a bigger cube which is having a net volume of V plus delta V and a net increase in length by L plus delta L. So we can say that we'll start from the basic equations again, that is delta L is equal to alpha L delta T, that is equation number 1, and delta V is equal to gamma V delta T, that is equation number 2. And again the same procedure, that is delta V is equal to change in volume, that is final volume minus initial volume, which is nothing but the final volume is L plus delta L L plus delta L whole cube minus L cube. So L plus delta L whole cube is nothing but, that is, a plus b whole cube is equal to a cube plus b cube plus 3a square b plus 3b square a. That is a plus b whole cube. So you can just use that particular result here also and just say that L cube plus delta L cube plus 3L square delta L plus 3L delta L square minus L cube. So again, we are saying that since delta L is very small, all the power factors of delta L will be approximately equal to 0, which means delta L will be equal to 0, delta L square also will be approximately equal to 0, and plus L cube and minus L cube will cancel each other out, and the only remaining quantity is 3L square delta L, which is equal to delta V. Again, we are doing the same procedure, that is delta V is equal to gamma V delta T. So we can say that gamma V delta T will be equal to 3L square delta L, and delta L is alpha L delta T. So we can say it is 3L square alpha L delta T. Delta T and delta T cancels each other out. 3L square into L. Again, L square into L is L cube, which is nothing but the volume of the cube. So we can say that gamma V will be equal to 3V alpha. V and V cancels each other out. Gamma is equal to 3 times alpha. And that is your final result. So we proved that, or simply we can just say that alpha is equal to 2 times beta and alpha is equal to 3 times gamma, or simply the particular ratios will be in the order of 1:2:3, and that is the relation between alpha, beta and gamma. So I hope you have understood everything about what is expansion, temperature scales, and what temperature exactly is. So that is all for today. I'll see you all very soon with remaining topics. Until then, thank you.